My name is Hui Chen, and I'm happy to present the work here. This work is a collaboration with multiple co-authors. There are Xiaojun Xu. Okay. There are Xiaojun Xu, Xue Zhicao, Weinan Zhang, Yongyu from Shanghai Jiao Tong University, Chang Liu, Dang Song from UC Berkeley, and Teng Ren Kun Wu from TouchPal Incorporated. I'm sure many of you have received some sort of unwanted calls. Some are annoying and some may result in financial loss. We refer to them as malicious calls throughout the talk. Some previous work target at voice over internet protocol services, and they rely on network infrastructure information. They collect data from the routers and servers and make a prediction. But such information is not available when we consider a traditional telephony network. So the question is, if we don't use network infrastructure information, how can we make a prediction? The main contributions of our paper is that we provide a client-side solution to prevent malicious calls. We built a mobile app called TouchPal, and we did a measurement study on the data set collected with this app, and then we use machine learning techniques to do malicious call number prediction. TouchPal is a client-side solution, and by saying client-side, I mean it doesn't use the network infrastructure information, and the benign calls just pass through it, and the malicious calls will be prevented by generating a warning to the user. A blacklisting approach is used here. When the user hands up a phone, he can label the phone as malicious, or we can, this app may also actively prompt the user to tag a suspicious call. So after we collect a bunch of such tags, we can generate a blacklist. If a number is labeled by more than m different users, we will put it into the blacklist. Please pay attention to the label threshold m here, as we will use it later. After we generate a blacklist here, if a phone number in the blacklist calls any other users again later, we will just either block that call or warn the user. This approach is simple and effective, but there is one major challenge. That is, we want to avoid false positives. So we will need much feedback before we label a phone number as malicious. And here, this threshold m may range from 30 to 100, so there will be 30 to 100 unblocked malicious calls. So we would want to improve this with a machine learning algorithm, and we want to predict malicious calls before it has disturbed too many users. There is one challenge, that is we have limited information. If you consider email spam detection problems, we have the header information, and we also have the content information. But for telephony spams, we have the header information, but we don't have the content or network infrastructure information. So our goal is to find some indicative statistics for accurate classification. We collected a large-scale call log dataset during 3 months in 2016 in China. This call log dataset contains over 9 billion call records. They are all labeled. A call log is labeled as malicious if that caller in that call is in our blacklist. Otherwise, it's benign. So we did some measurement study over this dataset, and I will show a few results here. This is the daily call volume in October 2016. Note that the first 7 days in October is the national holiday in China. So there are more benign calls during the first few days because people may send in greetings to each other. But for malicious call volume, this is substantially less than usual. Also, you can notice that during the weekends, the malicious call volume almost halves. We also notice a similar pattern when we consider the hourly call volume. It's a similar work and rest pattern. It seems that the malicious callers are most active when it's work day and work hour, and they go to rest when it's holidays or non-working time. This is the distribution of phone numbers over the number of calls they make. You can notice the three curves here are very different. If you look at the tail there, they are the phone numbers that are making large number of calls during 3 months. The percentage of malicious callers in that range is much higher than the percentage of the other two categories, and this is consistent with our common sense. You can find more results and explanations in the paper. So with these statistics, we can transform them into distinguishable features. Suppose the current time is T10, and currently a phone number A calls a user U5. So that call record is shown in the pink table here. And we also retrieve a bunch of call records from the database, and we call them historic records, and they are shown in the blue table. This is an overview of our feature set, and it contains two parts, the current and the historic. We retrieve one feature vector for each call record. So there is one current feature vector, CT, for the current call record, and there are multiple historic feature vectors, H1 to HT-1, for each of the historic records. Also, notice that for each of the feature vectors, there are two parts. One is static, and the other one is non-static, and I will explain them later. Here is the static feature vector. The static part of the feature vector is just a subset of all the attributes in our call records. And I've highlighted them in yellow and blue there. And for the non-static feature vector part, we consider the relationship between the call logs, and the color shows their belongings. For example, if you see the green gap to next feature, it's a part of the historic feature vector, and it means the time gap between two consecutive calls. And the red feature is redial, is part of the current feature vector, and it means whether the current call is a redial by comparing this call to the last call. And with all these features, we can use them in machine learning algorithms, and as this is a binary classification task, we report the AUC scores here. These are AUC scores of 6 different models on the same province. We have 3 months, so we split them into training and test dataset. And you can notice here the AUC scores of all 6 models are very high. They are very close to 1, and this is very good. The random forest model here achieved the best AUC. And we also test these models on the data of a different province to see if they transfer well, and the results are pretty nice. You can refer to the paper for details. Also, we did an ablation analysis on the features. The first line "or" here indicates that we use all the 4 blocks of features, and minus his means we exclude the historic feature vectors, and we just use the yellow and the red blocks of features there. And minus NS means we don't use non-static features, and basic, we only use the yellow feature box there. As you can see, the performance is best if we use all the features as expected. But if you want more efficiency in computation, you can just use the current static and non-static feature vector, and we don't consider the historic features. And you can see the AUC scores are very similar to if we use all the features. This is a visualization of a decision tree trained with XGBoost package. The red nodes denote that the prediction is malicious, and the blue is benign. You can see from this graph how this tree model makes predictions, and it provides explainability. Also, using these trees, we can count how many times one feature is used in the whole model. And they are shown here. These are some of the top used, the most frequently used features in the decision tree models. And on the right is the AUC scores. And if we just use the top 10 features, just use the 10 most frequently used features, the AUC scores are reported here, and you can see the AUC scores doesn't drop very much. It means the top 10 features are very indicative. Also, we want to measure the performance to detect malicious calls, and there are two requirements. The first one is that an effective detector should not block benign calls, and the second is that it should predict malicious calls as early as possible. And so we introduce a new metric. We call it first prediction at label threshold M and benign precision P. FP at MP means the number of calls we have to see before we can predict a number to be malicious. If we want to ensure that the precision for the benign calls is high. These are the AFP, the average first-time prediction results. And you can see if we make sure the precision for the benign callers is 0.9999, and the AFP is around 3 to 4, and this is very low compared to the common label threshold, which is between 30 and 100. So this is a reduction of over 90% of unblocked calls. So to summarize, we propose a client-side solution on TouchPal to detect and block malicious calls, and we conduct a large-scale measurement study over the billions of call records we collected using the app to understand the characteristics between benign calls and malicious calls. And we propose a set of features and fine-tune them to build effective machine learning models to detect malicious calls. Thank you. I'm happy to take questions.
Very interesting talk. We have time for a few questions. Maybe we can start.
Nice talk. I'm Hao Tian from University of Texas at Arlington. And you collect a large of the database about the malicious call. But I don't know how do you ensure the database is accuracy? Because from your talk, you said if the user is not labeled your call is the malicious call, it will be labeled to the nice call. But how do you ensure the user always label the malicious call at the accuracy of your database?
Actually, although we only use 3 months of data in the work. This app has been running for many years, and there are millions of users, and the labels set is very large, and we also collect information from the internet. For example, some people will post like this number has called unwanted calls to me or something like this. We have combined all these information to make sure we label the label set is as complete as possible. Does this answer your question? Thanks.
Hi, I'm Brad Reeves from NC State. Great talk and very interesting work. I'm glad to see that this problem is getting more attention. So my question has to do with the fact that, unfortunately, just because of how the phone system works, you can only really use features that are related to caller ID. And that means that, unfortunately, there's not much that you can do about call spoofing, caller ID spoofing. I'm wondering if you could maybe tell us a little bit more about how you might think that that affected your results. Maybe, for example, how many of the calls in China malicious calls are using caller ID spoofing? Because I know that in the United States, almost all of my calls are spoofed.
Sorry,
Let me rephrase. How much of the calls in your data set do you think are spoofed? And is caller ID spoofing a bigger problem in China than in the US?
Oh, actually, we didn't consider the caller ID spoofing attack in our work, and that is left as a future direction, because we only use the caller ID to identify a malicious call number. So actually, if it's a spoofing attack, we cannot identify it.
Okay, thank you.
Thanks.
Hi, good morning. I'm Rajorshi Gupta from Avast Software. And very nice talk, very nice work, and I was very impressed by the 9 billion records being evaluated. So you have two types of features. One are the current features and the other are historic features.
Yeah.
How long does it take to extract the historic features? Because you need to defend it as the call is coming in.
Yeah, we evaluate the running time in the paper, and I think it's like several milliseconds, and I cannot remember the specific details. Maybe we can offline.
Okay, come by. We can chat offline.
Yeah.
Okay. Well, thanks for the very nice work. So I have a question about what kind of data do you actually collect from the smartphones? What kind of data the app that you have collects? So I think your paper, if I remember well, you mentioned that you have 6 labels, I think, that the users can provide. 5 are decided by you, but 1 the users are free to choose.
Yeah.
I was wondering if you can comment about what kind of labels do the users give you besides the ones that you decided?
Maybe. Actually, there are 6 different labels, as you said.
Right.
We use 2 of them as malicious in this work, and the others as benign. The 2, one is fraud, and one is, I think, harassment, and the other, the other 4 are used as benign.
But I think in your paper you mentioned that 5 of the labels are set. 2 of them are malicious and 3 are benign. And then if I'm not mistaken, you say one of the labels is left free for the user to choose, basically, to specify. And I was wondering what type of calls will the user share with you, and how will they label them? Benign calls, probably.
Maybe we can chat offline.
All right.
Offline, yes.
Right. Right. Yeah, I was curious for the set of data that the users labeled something different, what that different may be. Okay. All right.
So very interesting. Let's continue this offline because there are a couple of more questions.
Yeah,
So.
thanks.
Hi, I'm Arslan Moussania from Princeton University. I actually had a question about related work. Do you know if there's any other non-machine learning based algorithm for detecting this approach, and what is the benefit of using machine learning? Because it seems like if, for example, 100 of users say that this number is malicious, so we can probably, just mark that as malicious. So what other parameters do we have here in your data set that you think that will help us, increase our detection accuracy? So why using machine learning for this problem?
So your question is, why do we use machine learning?
I mean, for example, you had like a couple of features, for example, the duration of the call,
Yeah.
As well as, the time of the call and so on and so forth.
Yeah.
So the time of the call, so it will help us if we have a phone number, for example, in the morning, so it's malicious, but at night it's not malicious. So do we have like such cases? Like in what cases, for example, you think that specific feature, for example, the time of the call will help us to detect the maliciousness of a call?
Maybe that visualization of the decision tree can answer your question. I think you are asking how is the model making predictions based on the features? Is that right?
I see. So, I see. Thanks.
Okay, one final question on the.
Thank you for the presentation. I'm wondering if you can say anything about the risk of maliciously labeling a number as malicious. So trying to block some normal number by getting a few friends to label something as malicious. If you can say anything about that.
So one of the previous talks in this session was about poisoning attacks, right? It's they can do it, right? So is this a threat to your approach?
Yeah, maybe the malicious persons can label a benign call as malicious, but they will need to they will need like 30 to 100 labels in order to make a benign number malicious, and I think this is pretty costly, and they may not want to waste that time, and because they have to register a user ID on the platform before they can label that caller, that benign caller. So I think also for in such a large data set, if they only poison a few benign numbers, I don't think they will be a big influence on our performance. Yeah.
Sounds like a challenge for the Northeastern team. Let's thank the speaker.
Thank you.